Pet Triple Crown. That's really dropped off because that's where my car will be after.
It's tricky, Chris.
Why not?
Let's go to page 4. Highlight a few problems there. Uh, 14 is a kind of a good problem for us to see what AP style multiple choice problem could look like. So this requires a little bit of knowledge of both what the piecewise function is doing from function perspective and also from a derivative perspective. So 14 says, let f be the function defined above, where c and d are constants. So again, we got to treat c and d the same way that we do numbers, right? So imagine this was like 5x plus 4. Imagine this is x squared minus 5x, fix x, right? So don't let those letters throw you off. Just pretend like it's a number, and however way you treat a number derivative-wise, that's the same way you're going to treat those letters. Okay, if f is differentiable, what is the value of c plus d? So we know that this graph is split on either side of 2. So I'm not going to pretend I know what this graph could look like, but it's going to be a line. The other side is going to be a curve. But we do know something. We do know that f is differentiable at 2. So that means that not only is the graph connected, right, it's also going to be what? I'm not drawing it very well, but it's also going to be what? What does differentiable mean? That's part of it. Continuous, but differentiable has to do with slope. What's differentiable mean?
No sharp turn.
No sharp turns, right? That means slope exists everywhere. That means at 2, the graph is going to have a smooth transition from one slope to the next. Sudden sharp turn. So even though that's a line, this is probably going to be matching that exact same slope, and then it's rising. So I'm not drawing it perfectly, but I want us to kind of see that it is a smooth curve. So what we do know is that means these two graphs, they must share the same what at 2? What did they share? Slope. Okay, and they share the same what? Point. Yeah, they share the same point and they share the same slope. So what does that mean for us algebraically? That means that if they share the same point, that means we can set equations equal to each other. Right? They must share the same y value. But that's where that portion comes from. And because they share the same slope, we can also set their what equal to each other. What's related to slope? What can we find that is related to slope? Derivative. Yeah, we can also set the derivatives equal to each other. Okay, so we'll let the cx plus d equal to x squared minus cx. Okay, we know that they must share the same y value at 2, so I can replace every x with what? What can I replace x with? What do we know about x?
It's 2.
2. Yeah, so replace the x with 2. So 2c plus d equals 2 squared minus 2x. Sorry, minus 2c. I said replace the x. Okay, so let's see how far we can get just with this equation alone. I get 4c plus d. See, 2c plus d equals 4 minus 2c. So 4c plus d is equal to 4. Okay, so we can pause off that because we still have two unknown values that we don't know. Let's move to the derivative, right? We can also set the derivatives equal to each other. So what's the derivative of cx plus d? Imagine this was 3c plus 4. Just c, yeah. So c is equal to, what's the derivative of x squared minus cx? 2x minus c, yeah. So this is a little bit easier. Well, we can also replace x here with what? 2, okay. So if I size, I get 2c is equal to 4. Solve for c equals 2. Thanks. And if I have the c value, then I can use that to plug in the other equation that I have in store. So replace 2 in for c. A plus d equals 4, so d equals -4. I have my c value, I have my d value. What they want is they want c plus d. So 2 minus 4 is -2. Okay, 15, what is the average rate of change? So average rate of change is just slope. So all we do is we just do change in y over change in x. There's no calculus involved here. This is just finding slope. Okay. So 16 tangent line, we can use the two order pairs to get the slope, and whatever that slope is, that's going to be the slope of the curve at that point because the line is tangent. Let me review implicit with you. So this is 18 and 19. So implicit is where we find the derivative of each variable, but as soon as we come across y's variable and we find its derivative, we attach a dy dx. But there's something else besides the fact that y is out of place, and we got to do dy dx. We also have to make sure we apply what? Derivative wise. There's also another process. We have to make sure we make sure. Something about this 4xy here. Product rule, yeah. So we see x and y being multiplied, so we got to go through product rule. So let's go through that process. Okay, I'm going to rewrite this as 3x squared minus parentheses 4xy equal to 1. Okay, I'm going to take care of product rule inside the parentheses first, and then I'll distribute the negative through. I want to forget about that negative there. So here's my. All right, so go with your power rule here. First, 3 squared becomes 6x. Okay. F prime g plus fg prime. So f prime times g plus f g prime. So y's derivative becomes dy dx. Then what does the 1 become? 0. Okay. So there's only one y variable here. So that means there's only one dy dx that should show up. But now we can distribute the negative through and solve for dy dx. Okay, so dy dx is going to be 6x minus 4y all over 4x. All right, however, I'm trying to find the slope here. So I gotta, if I want to plug 1 in, I'm still left with a y. So what I need to do is I may need to plug 1 back into the original equation, get the full order, and then plug in to find the slope. So I'm going to plug 1 in, see if I can solve for y here. So I get y is equal to 1/2. So my derivative, I know my full order pair, which is 1, 1/2. And I can go into my slope formula. So 1 in for x and 1/2 in for y. So 6 minus 2 is 4. 4 over 4 is 1. So my slope at 1, 1/2 is going to be 1. Okay, another implicit for number 19. Because we see y's all over the place here, so we got to keep track of our dy dx's. So again, we have 2 y variables, so we are expecting 2 dy dx's. Again, there's product rule that's going to show up. So we go through that process again. Every time we find the derivative, we got to attach the dy dx. When we get to the 2xy though, after we go through product rule, we want to make sure we distribute that negative through. And then combine all the dy dx's together, replace all the x's and y's with 3 and 2, and we can get to our slope, which is 4 over 9. Okay, page 5, let's review some related rates. So with related rates, we know that if there's time involved, we have to attach a d over dt for each of our variables. So here it says radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. In terms of the circumference, what is the rate of change of the area of the circle? It's in square centimeters per second. So we have 2 equations available that we can use here. We know that there's a reference to the area of a circle. There's also reference to the circumference of a circle. So let's start with those, right? So we know area is pi r squared. You guys remember what circumference of a circle is? 2 pi r, right? If you forget that, but you still, if you know area, the derivative of area is your circumference. So 2 pi r is circumference. Okay, let's just find the derivative. See if we can get that out of the way here. So if we want to find the derivative of area, we know that there's all these references to information about rate of change of area or radius there. So when we find the derivative, we have to attach a d over dt for each variable. So a becomes what? But there's t involved. So how do we write that? dA, what? dA over dt.
Okay.
Yes.
Sorry, I'll walk it to you. I just don't know what anyone looks like because I've never had A's and B's, so I'm
Okay.
sorry.
Okay, pi r squared becomes. We find the derivative first, then we attach the r's additional variable there. So pi r squared becomes what? 2 pi r, and then we need to attach dr over dt. Yeah. All right, so we have that out of the way. Let's see what we can gather from the problem here. It says radius is decreasing at a constant rate of 0.1 centimeters per second. What can we assign that to? What is that talking about? Close, definitely radius related. Yeah, so we see there's time involved, right? Centimeters per second, so you know it has to be something involving t, so that's where the dr/dt comes in. Is it just 0.1 or do we need to make an adjustment? Decreasing, right? So negative 0.1. Okay, in terms of the circumference, what is the rate of change of the area? So we just want to find dA dt. So to find dA dt, we can replace dr dt with negative 0.1. Now they say in terms of circumference, so is there something that we can replace with circumference? Yeah, this whole thing can be replaced with what? With c. And also, if we look at our answer choices, right, everything starts with c. So any time that we can take our and replace it with the variable that they're asking for, then that will help lead us to our answer. Okay, answer choice B. Okay, number 2. The radius of a circle is increasing. At a certain instant, the rate of increase in area is numerical to twice the rate of increase. What is the radius of the circle at that instant? So again, we're playing with the same equations, pi r squared and 2 pi r. Let's go ahead and find each derivative and then and see what we can do from there. So just copy what I did from above, right? dA dt. Okay, let's find the derivative for circumference with in relation to time here. So c becomes what? So look at what we did with A. What do you think we can do with C? Yeah, dc over dt. Okay, 2 pi r becomes, what's 2 pi r's derivative? Good, so 2 pi, because r is a degree 1, so we know that r is going to go to will drop out, but we are finding r's derivative, so we do need to include a dr dt. Okay, they don't give us any numbers here, so let's see if we can create some relationship here. It says the rate of increase in the area is twice the rate of increase in the circumference. So can we create an equation based off of that? What is the rate of increase in area? So we can say dA dt is equal to what? Say it again. Twice the rate of increase in circumference. So dA dt equals
2 dc
good
dt.
2 dc dt. Yeah. So what is the radius? So we just have to kind of search for an equation that can help us cancel a bunch of things out. So we know that dA dt is twice of dc dt. So I could basically set these equal to each other, or just replace dA dt, dc dt with r's, right? So let me kind of color code what I want to do here. So I'm going to replace this in for this. Then this in for that, right? And if we can get our equation with r showing up, we can then solve for r. So I'm just make a substitution here. dA dt gets replaced with 2 pi r. dc dt gets replaced with 2 pi dr dt. Okay, dr dt cancels out. The 2 pi's also cancels out. So I'm just left with r equals what? 2, yeah. All right, number 3. If the base of increasing at a rate of 3 inches per minute while its height is increasing at a rate of 3 inches per minute, which of the following must be true about the area of the triangle? So we know this related rates because we see a bunch of time references. So we know that this is dealing with the area of a triangle. What do you know? What's the area of a triangle? What's that formula going to be?
Based on type and blend.
Okay, so I'm going to say 1/2 base times height. Okay, if I want to find the derivative of this, I'm going to get all the dA dt and all the time variables to show up. What else is involved if I want to find the derivative? Product rule, right? I got to do. I can't just say dB dt and dH dt. That multiplication process is forcing us to go through rule. So I'm going to go through product rule there. See if we can spell everything out here. So A becomes dA dt. To F prime G and F G prime. Okay, what's the derivative of 1/2 B? Yeah, every variable has a time component, right? All right, G is going to stay the same. Back to F. G prime, what's G prime going to be? Okay, let's assign some variables here, or some values to variables. If the base of a triangle is increasing at a rate of 3 inches per minute, that's dB dt, positive 3. While its height is decreasing at a rate of 3 inches per minute, dH dt, any adjustment there? We want that to be what? -3. Which of the following must be true about the area of a triangle? So let's just plug this in and see what this will get us down to. So I have 3/2 h minus 3/2 B. Okay, so the rate of change of the area is going to be this formula here. So it says, which of the following must be true now that we have this to help us decide which is appropriate. A is always increasing. So is that means dAdt must be always positive. Can we guarantee dAdt is always positive? Not if B is larger, right? If B is larger, then this is going to force to be negative, then my rate of increase of area is going to be decreasing. So we know this is not always true. A is always decreasing, not always true either. If H is larger, then B, then our equation will be a negative derivative there. A is decreasing when B is less than H. A is decreasing. Right. So it's not quite true either, because if B is smaller than H, then this is going to end up being a positive value. So that's not going to quite be decreasing. So we have to kind of play with these numbers there to see which one is always true. A is decreasing only when B is greater than H. This is true, right? If B is larger than H, then that's going to force the negative to be more than the positive, and that will give me my dAdt to be decreasing. Yep. So it's going to be, and we know that E is not true. A remains constant. That means dAdt is going to be 0. But dAdt is only 0 if H and B are the same, but we don't know if H and B are always going to be the same. We don't have enough information to claim that. Okay, number 4. The radius of a sphere is decreasing at a rate of 2 centimeters per second. At the instant when the radius of the sphere is 3 centimeters, what is the rate of change in square centimeters per second of the surface area of the sphere? And the surface area will be provided for you if they ask you to use it. So related rates, time is involved. So we need to include the derivative there. So S is 4 pi r squared. Let's find the derivative, get all of our time components to show up. Okay, so S becomes what? Four pi r squared becomes 8 pi. Is it 8 pi dr dt or? Yeah, we find the full derivative first, yeah, and then the tangent dr dt. Okay, so that's the only calculus in the problem, just to get from here to here. The rest is just identifying values and plugging in. The sphere is decreasing at a rate of 2 centimeters per second. What is that referring to? Okay. Anything special about the RDT? Any adjustment? Negative, yeah. At the instant when the radius of the sphere is 3 centimeters, so this is just the radius, there's no time component here, just r equals 3. What is the rate of change of the surface area of the sphere? So we're looking for what? dSdt. Okay, so now it's easy, right? We could just put everything in and make a bunch of substitutions and solve for dSdt. Okay, try that. Good. Yeah, so R gets replaced with 3, dRdV gets replaced with -2, multiply that together, -48 pi. Now, just want to talk about units for a second. We're talking about surface area over time. So focus on the word area. Area is a 2-dimensional unit. That's why centimeters squared. Time is per second. I know it's not referenced here, but if it's free response and they're asking for units of measure. I want to make sure that we know how to find those units. Let me review a very particular type of related rates. This is 6. Okay, so there's a triangle within a triangle here because the shadow and the person is going to form a smaller triangle, and the edge of the shadow is going to form a larger triangle. So I like to build out the triangle this way. We know that the person and the lamppost, they're not going to change in terms of their height. So those are the constants. So 6 feet tall, 15 feet tall for the street light lamppost. And then go ahead and put X and Y here. Okay. So we're going to create a proportion equation. And then once you have that equation, then we can cross multiply and we can find the derivative. So we can say this, the two triangles in play is small triangle and large triangle. The height of the small triangle is the height of the large triangle as the base of the small triangle. What's the base of the small triangle? Y is to the base of the large triangle. Close. X plus Y, yeah, X plus Y. We want to add these two lengths together to get that base. Okay, so if you can get to this point, then the rest of the equation problem gets a lot easier because you're just cross multiplying, finding the derivative, and then plugging information in. Okay, so if I cross multiply here, this is really the equation that I'm going to find the derivative for, but I would like to get that cleaned up before I work on the derivatives there. So 6 X plus Y. Okay, let's clean up as much as we can, get all of our like terms to come together. Okay, so now let's find the derivative. Every variable gets impacted by time. 6x becomes what? Good. 9y becomes 9 dy dt. Okay, let me define some of these variables for us. So dx dt is representing the rate that the person is walking away or towards the lamppost. So it's the rate of change of the person walking. Dy dt is the rate of change of the length of the shadow. So if you look at that bold portion there, that's y, that's the length of the shadow. As person is walking towards or in a way, that shadow is going to be changing its length. So dy dt is the rate of change of the shadow. And if I add the two rates together, dx dt and dy dt, if I add how fast a person is walking and that person and the shadow is also increasing at its own rate, if I add the two rates together, I'm going to get how fast the tip of the shadow is moving in relation to the ground. So the tip of the shadow is going to be impacted by how fast both the person and the shadow is moving. So it's two different rates at the same time. So we know that the person is walking 4 feet away from the lamppost. So that's going to be a +4 because the distance between, not because he's moving right, but because that distance X is increasing. The distance between him and the lamppost is increasing. What is the rate at which person's shadow is lengthening? We're looking for dx dt. I'm sorry, dy dt. So this problem is not asking for the tip of the shadow, it's only asking for the length. So if I identify dx dt as 4, replace 4 in for dx dt, and I should have to solve for dy dt, and I get 24/9, which is 8/3, or 2.67. Okay, let's do number 6. So number 6 says, answer is B, by the way. It says the graph of a function f is shown. Which of the following could be the graph of f prime? So let's create a sign line off of this. Now this is the original graph. So whatever you see is what you can expect from the slope and the concavity. So I'm going to put 1 and -1 here just so I can have some frame of reference. If I create a slope sign line, again, this is not the derivative graph, so there's no need to make any adjustments. Whatever the graph is doing, it can just tell. So in this case, where's my relative max, relative min? Yeah. So I'm just going to follow the slope that I see in front of me. Right. So slope is rising, slope is falling, slope is rising. And then my f double prime, what do you expect the point of inflection to be? Remember, this is the original graph here. So wherever you expect your point of inflection to be is going to be where it will be. Where does the concavity change? Or where does it look like it changes? 0, yeah, concave down, the concave up. So if we want to create a derivative graph out of this, I want my derivative graph to look like this, where positive slope is above, negative slope is below. Any x-intercept is going to have to be where the slope is 0. Right, so I know those are my anchor points. My f prime graph has to go through those points. Where do I want my graph to start off? Above or below the x-axis? Above. So it's got to come down to hit that point, right? That's my anchor point there. So it's got to come down to hit that point. And then between -1 and 1, where do I want my graph to live? Below. So it's got to come down and go back up, right? Because there's a point waiting for it, because I know my graph's going to be connected. And then to the right of 1, above, right? And this should also match what we know about the second derivative graph. Point of inflection is going to be the peaks or valley of the graph. We see that there is a valley at 0. Concave down would indicate that my f prime graph is decreasing. So we see that to be true. And then to the right of 0, concave up, positive slope. Yeah. Answer choice.
Will it ever ask you to go like from the regular graph to the like double prime graph, like transfer over to X?
Probably not, but we could still do it though. If we're trying to look at the second derivative graph, it'll look like this. Above is concave up, below is concave down. It's got to go through 0. So it starts below and it goes above. So it's going to be a linear graph like that. And it kind of makes sense because if something is x cubed, then it becomes x squared, then it becomes x. So that also makes sense from a derivative standpoint. Okay, I'm going to shorten the homework. Your homework is just going to be pages 5 and 6. You've already done most of 5 and 6. Just have to finish off 6, and tomorrow we'll do 7 and 8 together. All right, come get your phones. Okay, thanks.